we're going to continue solving inequalities. Most of today will focus on how to test different regions within the inequality, and we'll do that using a couple different methods. But the first thing that we need to determine are key numbers within our inequality, and on these types of problems, they will be the x-intercepts or the zeros or the roots. So the x-intercepts of the graph. And depending on the type of polynomial that we are given, we can factor. If it's quadratic, you can use quadratic formula. Otherwise, you can solve for x by undoing all of the numbers around it and get x by itself. But for this problem, I think the easiest method is going to be to factor rather than use quadratic formula. So we're going to figure out what multiplies to negative 32 that adds to positive 4, and that would be positive 8 and negative 4. And we're just going to bring down the less than 0. So if we think about, once we find our key numbers, we know we're going to set x plus 8 equal to 0. We could just solve that in our head. We know that's going to be x equals negative 8, and then x equals positive 4. So those are our key values. I'm going to put, think of a number line here, negative 8 to 4. And then we just need to come up with some number that's between negative infinity to negative 8, and then some number that's between negative 8 and positive 4, and then some number that's between 4 and positive infinity. So if we look back at the original inequality, it says that our goal is to have values that are less than 0. So not equal to 0, but just less than 0. So that means if we were to plug in exactly negative 8, that would not work. So that would be like an open circle here. 4, if we plugged in exactly 4, that would be equal to 0. That would be an open circle there. But now we need to know which of the 3 sections is actually going to be part of our solution set. So we're going to test a different value that's within each of these intervals. So I would suggest picking like the easiest number that you can think of, plugging into your original equation or the factored version of your equation, and see what you get. So if you pick a number between negative 8 and negative infinity, that would be like maybe negative 10. So I'm going to go back to my very original equation. So if I have negative 10 squared plus 4 times negative 10 minus 32, I've got 100 plus negative 40 minus 32. That's going to give me 28. But I don't even really need to know, is this number actually 28? I just need to know, is the number greater than 0 or less than 0? And that number is positive, right? So our goal is to look for numbers that are negative. So this section here, the negative infinity to negative 8, will not be part of our solution set. And then if I test a number between negative 8 and positive 4, I'm going to go with 0. I think that's the easiest number to always plug in. Or if 0 is part of your interval, then use that whenever possible. So 0 squared plus 4 times 0 minus 32 is going to be 0 plus 0 minus 32, which is negative 32. And again, I don't really have to figure out the exact number, but I know that it's going to be negative. And that's good. So this is part of the solution set. So in my solution set, I would shade in between negative 8 and positive 4. All right, and then I just have to test one more region. So some number bigger than 4, I'll go with 5. And I just need to do 5 squared plus 4 times 5 minus 32. So that's 25 plus 20. It's 45 minus 32. That's 13. And that is positive. So that is not part of the solution set. So I will not shade in the number line for the 4 to infinity section. All right, so I need to go through and finalize my solution, right? So I already made sure everything had the zeros on the right side and everything else was on the left. I found my key numbers. Those were negative 8 and 4. I listed the intervals in between the key numbers. I check the intervals, right, and see if they're positive or negative. It says convenient test numbers. Pick the easiest number that's in that interval. And then my final solution is going to be the part that I shaded up here, which is -8 to 4, not including -8 and not including 4. So I'm going to use parentheses for that one. If it was less than or equal to 0, then I would include the endpoints. So I would include -8 and +4. All right, so that's our first example. Basically, every problem is going to be very similar to that. So for number 1, we have to find all the key points, right? So I'm going to try to solve, and I think that factoring out a GCF will make solving easier. So if I take out an x, I get x squared plus 13x plus 42, which is greater than 0. And then I have a quadratic that is definitely factorable because I can come up with two numbers that multiply to 42 and add to 13. That would be 6 and 7. And notice that you have a cubic function, so you have 3 solutions. So those are going to be my 3 key points that I'm going to put on a number line. And I'm going to put those in order. So -7 is the smallest, then -6, and then 0 is the biggest. All right, so I need to come up with values that are between each of those little 4 sections, right? So numbers that are between -infinity and -7, some number between -7 and -6, some number between -6 and 0, and some number between 0 and infinity. All right, so to solve this one, it says solve by using the test point method. So we're going to test different points. One other way we could do it is we don't have to necessarily plug in to the original equation. We could plug it into the factored equation, right? That might help us figure out the numbers a little bit better or faster. So I'm going to go with the number probably -8, -6.5, because there's nothing else really between -6 and 7 that would be easy to do without a calculator. And then I'm going to go with maybe -1. I can't pick 0 this time because 0 is my endpoint, and then I'm going to go with +1. So I'm going to plug it into this second version of the equation. So after I've factored out the GCF and factored out the quadratic, I've got that. So if I plug in -8, -8 plus 6 is going to give me -2. -8 plus 7 is going to give me -1. So I don't even really have to figure out the actual solution. I just need to know, is it positive or negative? I know negative, negative, negative is going to give me negative. All right, well, what are we looking for in our final solution? We need something that's greater than 0. So we're looking for positive. All right, so this would not be part of my solution set. All right, then I'm going to test -6.5. So I've got -6.5. -6.5 plus 6 is -0.5. And then -6.5 plus 7 is +0.5. So I've got negative, negative, positive. That's going to give me positive. So that is part of the solution. Okay, we'll highlight that part of the number line there. All right, moving on, we're going to plug in -1. So we got -1 times 5 times 6. That's going to give me a negative value. And that is not what I'm looking for, since I'm looking for greater than 0 this time. And then the last one I'm plugging in is 1. So we got 1 times 7 times 8. And that's positive, positive, positive. So that's going to give me positive. And that is part of the solution set. All right, so what do I want as my final solution? I want the 2 highlighted regions, and I just need to list those as intervals. So I'm going to go from -7 to -6. All right, so I'm going to list my highlighted regions as my interval solutions. So I have -7 to -6, and then I'm going to have a U for the union symbol, and then 0 to infinity. And no brackets on there because it's only greater than 0, not greater than or equal to 0. So all those key points, 0, -6, and -7, those would give me exactly 0. All right, for part B, we're going to use our calculator. So it says to sketch a graph of the polynomial. Now, I could use my original equation. I could use my factored version of the equation. Whichever one you want to substitute in or plug into your calculator is fine. So I'm going to go to y equals, and I'm going to type in x to the third plus 13x squared plus 42x. And then I don't type in anything about the inequality, so that's it. Now, before I do the graph, I'm going to try to do this by hand, and then we're going to check to make sure that we graphed it by hand. So if you don't have a graphing calculator, or if this is on the non-calculator part of test or quiz, then you can use this method for graphing. So I know that my x-intercepts are at 0, -6, and -7. So I know that my graph should cross through those two locations. I also have one at exactly 0. All right, and I also know that it's a cubic function. So if it's a cubic function, basically my graph has a shape where the endpoints go in opposite directions. There might be some kind of a curve within there. It can have at most 2 turning points, which is places where it changes from increasing to decreasing or decreasing to increasing. Since it's a degree of 3, 2 is the most amount of turning points. And since the lead coefficient is positive, right, positive x to the third, I know it has to end up going up and to the right, and it has to start off going down and to the left. So if I were to sketch that in general, my graph looks like this. All right, so let's hit graph on our calculator and see what it looks like. I could zoom out a little bit if I want to. Let's hit zoom out. And you can see that that's essentially the shape of the graph. It doesn't have to be perfect. We just need to see what's going on in the graph. But now we know also, we can identify on the graph where is the y greater than 0. So where is your graph above the x-axis, right? So the locations where it's above the x-axis are between -7 and -6, and then after 0. So looking only at x coordinates between -7 and -6, and then also between 0 and infinity. At -7, -6, and 0 itself are exactly 0, so that would not be your part of your solution set. So if you notice, you get the same exact answer. So that's another way to do it, is to just think about what the graph of the polynomial should look like. And so we might switch back and forth between looking at the graph, plugging numbers in. I think the graph method is actually the quickest. So let's try to do number 2 using the graphing method. This is a cubic, so we're going to look for 3 key points. Usually these are factorable, but this time there is not a GCF because there's not an x in every term. So we have to try another method of factoring. So for this one, we're going to try to factor by grouping. So when you factor by grouping, what you do is you look at the first 2 terms and you see, can I take out a GCF? So I can take out an x squared, and I'd be left with 3x plus 1. And then my second 2 terms, the -30x and the -10, look for a GCF there. It starts with a negative, so I'm going to take out a -10, and then see what's left over there, and we're left with 3x plus 1. And if these 2 binomials are the same, then that's good. We've factored by grouping, and we can take that out, and that leaves us with 3x plus 1 and x squared minus 10 is less than or equal to 0. And then for the x squared minus 10 part, I have to do x squared equals 10 and take the square root. And that would give me x equals plus or minus square root of 10. For the 3x plus 1 equals 0, that's going to be 3x equals -1, so x equals -1/3. All right, so these are my 3 key points. I should not circle those because those are not my solution, but those would be the things I would identify on my number line. And so I'd have negative square root of 10 would be about like a little less than -3. Then I'd have -1/3 over here. And then I'd have positive square root of 10. All right, but I think trying to pick out some numbers to test between negative square root of 10 and -1/3, I mean, I could pick -1, -2, or -3. It'd be okay. But let's just think of the graph. So we can graph. If we 3x to the third plus 10, no, just plus x squared minus 30x minus 10. And I can see what the graph looks like. So instead of thinking of this as a number line, we'll think of this as the 2-dimensional coordinate plane. And I'm just going to hit zoom 6 to go back to my standard window. So notice that you have x-intercepts at negative square root of 10, negative 1/3, and positive square root of 10. And just like before, it's a cubic function with a positive lead coefficient. So I know that my graph should generally look like a positive slope with some curves in the middle, and we can have up to 2 turning points. So if I know it has to end up on the upper right and go down and to the left, then in between there, I know it's got to change direction to get back to this 0, and it's got to change direction to get back to that 0. So that's a rough idea of what the graph looks like. It does go higher than 10 and lower than negative 10, but all we care about is where is the graph less than or equal to 0? All right, well, it's going to be exactly 0 at these 3 x-intercepts. And where is it going to be less than 0 is underneath the x-axis. All right, so to list our final solutions, we're going to say that it can be from negative infinity to negative square root of 10. Now, infinity always has parentheses, but this time we'll go with a bracket because we are including the number negative square root of 10, and then union. And then we're going to go with negative 1/3, including a bracket because there is a 0 at negative 1/3, up to positive square root of 10. And those are our 2 regions with a U symbol in the middle because that's the union symbol. It says basically the same process as polynomials. You're going to find test points, and you're going to identify true or false to decide if it's part of the solution set. The only thing is that our key numbers are not just where we have x-intercepts, but we're also going to find where the denominator equals 0. So not just where the numerator equals 0, but the denominator equals 0. So where your denominator equals 0 is where you would have a hole or an asymptote. All right, so for this first problem, we don't have to do a lot of solving, but my key point that makes my numerator equal to 0 is x equals negative 2. What makes my denominator equal to 0 is positive 5. All right, so we can test key points algebraically, or we could test with a graph. So we can probably do both methods for this one. It's not too bad. Let's start with the number line method. So we'll start with negative 2 and 5, and then we've got 3 regions to test. We've got negative infinity to negative 2. We've got negative 2 to positive 5, and we've got 5 to infinity. So don't pick the actual endpoints, but just anywhere in between there. So if I plug in maybe negative 3, 0, I like that number, and then 6. All right, so I'm going to plug in negative 3 plus 2, that's negative 1, over negative 3 minus 5 is negative 8. And we don't really care what the actual answer is, but we do know that that's positive. Our goal is to get anything greater than or equal to 0. So that sounds like that's good because it's positive. All right, and if I move on, then I'm going to plug in the number 0. So 0 plus 2 is 2. 0 minus 5 is negative 5. That gives me negative. That is not part of my solution set. So we're going to move on to the next one. So 6 plus 2 is 8. And then 6 minus 5 is 1. So that gives me a positive value. And that would be part of my solution set. All right, now since we do want or equal to 0, right, if I plug in actually negative 2, negative 2 would give me negative 2 plus 2 and negative 2 minus 5. So that would give me 0 divided by negative 7. So this would be okay. All right, I'm just going to plug this in to show that don't necessarily include all the endpoints just because it says greater than or equal to. So if we plug in 5 plus 2 over 5 minus 5, that does not give me 0. That gives me 7 divided by 0, which is undefined, which is, again, a hole or an asymptote. So that is not part of my solution set. So when you list your final solution, then I'm going to go with negative infinity to negative 2 with a bracket, and then union 5 with parentheses, not a bracket, and then infinity. All right, so what does our graph look like? Let's look at the graphing method. If you do this in your calculator, I would go to y equals and go alpha y equals and make it into a numerator and denominator template. So we've got x plus 2 on the top, and we've got x minus 5 on the bottom. And then if I hit graph, I'll do zoom 6. And you can see that something's going on around 5. 1, 2, 3, 4, 5. That's an asymptote. So what would make a whole is if we had maybe x minus 5 on the top and x minus 5 on the bottom, and they'd cancel out. But since there's only one binomial that says x minus 5, that's an asymptote. So my vertical asymptote is at x equals 5. And the horizontal asymptote is at 1. And the reason why it's at 1 is because if you look at the degree of the numerator, it's a 1. The degree of the denominator is a 1. And if you look at the lead coefficients, so when you have the same degree on the top and bottom, then you look at the lead coefficients, the coefficient of the highest exponent term, that's 1, and 1 over 1 is 1. So y equals 1 is your horizontal asymptote. So you can see, according to your graph, you've got two branches that go over here on the upper right. It touches a little bit below, and it goes to -2 as an x-intercept. So we'll go through that way. All right, so you got a branch on the lower right section there. But what we're looking at exactly is where is the graph above the x-axis. So it's above the x-axis here, and all of this is above the x-axis. So if you look at only x coordinates, right, -infinity to -2, and then +5 to infinity. All right, so you decide which method you want to do. You want to think about it in terms of the graph. Do you want to just test points? It doesn't really matter. You may or may not have use of a calculator, but you can always sketch a graph even without a calculator. All right, one more similar to this. We should look for our key points. So we're going to say, well, x squared minus 7 could equal 0. That would be any x-intercepts. And so that would be x squared equals 7, which is x equals plus or minus square root of 7. All right, so I think I'm going to show another method for testing points, but the other one that we have to solve for is x squared minus 16 equals 0. So that's going to give us x squared equals 16, and x is either equal to plus or minus 4. All right, so on my number line, -4 is my smallest number, then negative square root of 7, then positive square root of 7, and then positive 4. All right, so now I have 5 regions to test. So I need to test something between -infinity and -4, something between -4 and negative square root of 7, something between negative square root of 7 and positive square root of 7, something between positive square root of 7 and 4, and then something between 4 and infinity. All right, so I'm going to pick out some numbers to test. So let's go with maybe -5, -3, 0 is a good one for there. We'll go with 3 and 5. All right, but let's do this a different way. So I'm going to go back to the main screen, and let's test -5 first. So I like to store different values into a variable. So I'm going to do -5 and then hit the store button, and I'm going to store that in for x. So now I'm going to do alpha y equals, and I'm going to type in the expression. So I've got x squared minus 7 over x squared minus 16. All right, so I'm going to hit enter, and that gives me +2. So 2 is positive. What am I looking for in this problem? I want less than 0, so that would be a no, not part of my solution set. All right, now let's try -3. I'm going to store that in for x. And then I don't even need to retype my expression again. I can just plug the new value for x into the expression. If I go with my up arrow and grab the expression that I want, it tells me that I get -2/7. And that's negative, so that's a yes. That's part of my solution set. So I will highlight that part of the number line. All right, and if I keep going, now you could do 0 in your head, but since we've got the calculator out, we might as well just grab our expression again that we want. So we're going to plug 0 in there. We know it's going to be -7 over -16, which is +7 over 16, and that's positive. So that is not part of our solution set. All right, and then 3, that should be the same answer as -3 because everything's getting squared, but we'll just test it anyway. All right, so +3 should give me -2/7, which we determined earlier was negative, and that is part of our solution set. So we will eventually write in interval expression for that. All right, and then last one is positive 5. So I need to store that in for x and then go up and grab my expression. So this calculator storing of numbers into variables method, that might be fast if you have to test like multiple different regions, like 5 regions is kind of a lot to do by hand. So you could certainly do that on the calculator. All right, so positive is not part of my solution set. All right, so what do we actually want? We want values between -4 and negative square root of 7. Now this is just less than 0, so we don't want to include any endpoints at all. And then union with positive square root of 7 and positive 4 as my final solution set here. All right, last question. And this one's a little bit different. Notice all the other ones had greater than or equal to 0, less than 0. This one says less than or equal to 3. So one of the rules is that you have to have everything on one side. So I'm going to subtract my 3 so that it's less than or equal to 0. And that was one of the rules way over here at the very beginning. Write the polynomial on the left side with the 0 on the right. Okay, so now in order to combine 2x over x minus 2 and -3, I have to get common denominators. Well, right now my denominator is 1, and the other denominator is x minus 2. So what if I were to get common denominators? I could multiply by x minus 2. So I'm going to distribute a negative sign, so that'll be -3x plus 6. When I distribute the negative sign, that really becomes a plus, and then 1 times x and 1 times -2. And now I've got the same denominator, so I can combine these into a single fraction. So now I've got -x plus 6 over x minus 2 is less than or equal to 0. So key points would be something that makes my numerator equal to 0, so that would be x equals 6, or something that makes my denominator equal to 0, so that would be x equals 2. All right, so let's plug in some numbers in our 3 regions. We're going to make our number line from 2 and 6 being our key points. And then I need to come up with intervals, so -infinity to 2, 2 to 6, and 6 to infinity. So I'm going to plug in 0 over here, maybe 4 over here, and how about 7 over here? Go to this one, because we're going to look for, is it less than or equal to 0? All right, so I'm going to plug in 0 in there. So -0 plus 6 is going to give me 6, and 0 minus 2 is going to give me -2. So that gives me -3. So that's negative. What are we looking for? We are looking for less than or equal to 0. So that would be true. So we're going to include that section as part of our solution set. So we'll call that a yes. If I plug in 4, I get -4 plus 6. That's 2. And 4 minus 2 is 2, so that's 1. That's a positive, and that would be a not part of my solution set. And then plug in 7, I get -7 plus 6, that's -1. And 7 minus 2 is 5, that's negative, and that would be part of my solution set. All right, now what about our endpoints? If I were to plug the number 2 in, I get -2 plus 6, that's 4. And 2 minus 2 is 0, so that's undefined. All right, so 2 would not be part of my solution set, so we'll consider that an open circle. And then 6 should be part of my solution set, because that would give me an x-intercept. So if we just double check, that's -6 plus 6, that's 0. 0 divided by 4, that's 0. So yes, that's okay. Writing my final solution in interval notation, I have -infinity to +2. With parentheses because I'm not including the number 2. And then U for union, 6 I am including, so I'll put brackets around that to infinity there. And then that's my final solution. All right, if you have any questions on these problems, ask your teacher in class.